Somewhere in the universe right now, a star is dying, and in the next few seconds, it is going to collapse into something so dense that a teaspoon of it would weigh more than every car ever built on Earth combined. And it is going to bend space and time so violently that not even light, the fastest thing in existence, will ever be able to escape it again. And here is the part almost nobody tells you. That black hole is not going to stay the same forever. It is not some frozen, permanent scar in the universe. It is going to be born, it is going to grow, it is going to feed, it is going to feud with other black holes, it is going to spin faster than anything else in the cosmos. And after a length of time so long it makes the age of the universe itself look like a single afternoon, it is going to die, evaporating into nothing but a whisper of radiation, disappearing so completely that it will be as if it never existed at all. Black holes have a life cycle, birth to death, just like stars, just like people, just like everything else in this universe that exists inside the flow of time. And once you understand that full life cycle, black holes stop looking like simple cosmic vacuum cleaners and start looking like one of the strangest, most dramatic life stories in all of nature. To understand how a black hole is born, you first have to understand how a star spends its entire life fighting against its own gravity. Every star, from the moment it ignites, is trapped in a constant tug of war. Gravity is always trying to crush the star inward, compressing all of its mass toward the center. The only thing stopping that collapse is the outward pressure created by nuclear fusion happening in the star's core, where hydrogen atoms are slammed together with such force that they fuse into helium, releasing enormous amounts of energy in the process. For most of a star's life, these two forces are locked in a stable balance, gravity pulling in, fusion pushing out, and the star simply shines, sometimes for millions of years, sometimes for billions, depending on its mass. But this balance cannot last forever because a star's fuel supply is finite, and eventually the hydrogen in its core begins to run out. For a star significantly more massive than our own sun, roughly 20 times more massive or greater, this fuel crisis triggers one of the most violent events in the observable universe. As hydrogen fusion slows and eventually stops in the core, gravity, which had been held in check for millions of years, suddenly gets the upper hand, and the core begins to collapse inward with catastrophic speed. In a matter of seconds, a core that may have taken millions of years to form crushes down into an incredibly dense ball, triggering a shockwave that rips through the outer layers of the star and blasts them outward in a colossal explosion known as a supernova. For a brief period, that single dying star can outshine an entire galaxy of billions of other stars combined. But the explosion itself is not the birth of the black hole. The birth happens at the very center, in the collapsing core left behind after the outer layers are blown away into space. If the leftover core is massive enough, roughly more than about 3 times the mass of our sun, no known force in physics is capable of stopping its collapse. A slightly less massive core might stabilize into an ultradense object called a neutron star, where the pressure of tightly packed subatomic particles finally halts the crush of gravity. But beyond that threshold, there is nothing left to resist gravity's pull. The core keeps collapsing, smaller and smaller, denser and denser, past the point where matter as we understand it can even exist in any stable form, until, in a final act of gravitational surrender, it collapses down to a single point of infinite density that physicists call a singularity. Surrounding that singularity is an invisible boundary in space called the event horizon, the true edge of the black hole itself, the point of no return where the escape velocity needed to break free exceeds the speed of light. Cross that boundary, and there is no version of physics as we currently understand it that allows you to ever come back. This is the moment of birth. A star that may have burned brightly for 10 million years collapses, in a matter of moments, into an object so extreme that it effectively removes itself from the normal rules of the observable universe. This type of black hole, born from the death of a single massive star, is what astronomers call a stellar mass black hole, typically ranging from around 5 to several dozen times the mass of our Sun. It is, in cosmic terms, a newborn. And like any newborn, its first task in life is simply to survive and to grow. Once born, a black hole enters what might be considered its childhood and adolescence, a long period defined almost entirely by feeding. A black hole does not actively hunt or chase down matter the way a predator hunts prey. It simply exerts gravity, exactly the way any other massive object does, and anything that wanders too close, gas clouds, stray asteroids, unlucky stars, gets pulled inward. As matter falls toward a black hole, it rarely falls straight in. Instead, due to the conservation of angular momentum, it spirals inward, forming a swirling, superheated disk of gas and dust called an accretion disk. This disk is where some of the most extreme physics in the universe takes place. As material spirals closer and closer to the event horizon, friction and gravitational compression heat it to millions of degrees, causing it to glow furiously across the electromagnetic spectrum, including visible light, ultraviolet radiation, and most dramatically, powerful X-rays. This is actually how astronomers detect black holes in the first place, since the black hole itself emits no light at all. What we are really seeing is the final, blazing scream of matter as it is torn apart and consumed, just before it disappears forever beyond the event horizon. During this feeding stage, black holes can also unleash extraordinarily powerful jets of energy and particles, blasting out from their poles at speeds approaching the speed of light itself. These relativistic jets, driven by intense magnetic fields twisted up by the spinning black hole and its surrounding disk, can stretch for thousands of light years, far larger than the galaxy the black hole itself calls home. It is one of the great ironies of black hole physics that an object famous for trapping absolutely everything that crosses its boundary is also capable of producing some of the most powerful, far-reaching energetic outbursts anywhere in the universe, simply from the violent process of feeding. As a black hole continues feeding over millions or billions of years, it grows. A stellar mass black hole that starts out at, say, 10 times the mass of our Sun can, given enough time and enough available material, grow substantially larger. But the truly staggering growth happens at the centers of galaxies, where astronomers have discovered supermassive black holes, monsters ranging from hundreds of thousands to many billions of times the mass of our Sun. Nearly every large galaxy in the observable universe, including our own Milky Way, harbors one of these supermassive giants at its very center. Our galaxy's own resident giant, known as Sagittarius A star, weighs in at roughly 4 million times the mass of our Sun. And in 2022, astronomers using a global network of radio telescopes known as the Event Horizon Telescope successfully captured a direct image of it, a glowing ring of superheated gas surrounding a dark central shadow, the closest humanity has ever come to literally seeing a black hole's event horizon with our own instruments. How exactly supermassive black holes grow to such extraordinary sizes remains one of the most actively debated questions in modern astrophysics. Simple accretion of surrounding gas and stars, even sustained over billions of years, struggles to fully explain how some supermassive black holes reached such enormous masses so early in the history of the universe, within the first billion years after the Big Bang. Some researchers propose that early supermassive black holes formed not from the collapse of a single star, but from the direct collapse of massive primordial gas clouds, skipping the stellar phase entirely and starting life already enormous. Others point to galactic mergers as a key growth mechanism, since when two galaxies collide and merge, which happens with surprising frequency over cosmic timescales, their central black holes eventually spiral toward one another and merge as well, combining their mass in a single, dramatic event, and instantly creating an even more massive black hole. Our own Milky Way galaxy is, in fact, on a slow collision course with the neighboring Andromeda galaxy, and when that merger eventually occurs, Billions of years from now, the supermassive black holes at the center of each galaxy will likely spiral together and merge into one truly colossal object. This brings us to one of the most violent and scientifically important events in a black hole's life cycle, a black hole merger. When two black holes orbit each other closely enough, whether stellar mass black holes formed from dead stars or supermassive giants at the centers of colliding galaxies, they gradually spiral closer together, losing orbital energy in the form of ripples in the fabric of spacetime itself, called gravitational waves. As they spiral ever closer, the emission of gravitational waves accelerates dramatically, until, in the final fraction of a second, the two black holes collide and merge into a single, larger black hole, releasing an almost incomprehensible burst of energy, in some cases more energy in that single instant than the combined light output of every star in the observable universe. In September 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, made history by directly detecting gravitational waves from exactly this kind of event for the very first time, confirming a prediction Albert Einstein had made a full century earlier in his theory of general relativity, and opening an entirely new way for humanity to observe the universe, not through light, but through the literal vibrations of spacetime itself. Once a black hole reaches its mature, adult stage, whether stellar mass or supermassive, it enters a long period of relative stability, sometimes lasting for many billions of years, continuing to feed opportunistically whenever matter wanders close enough, occasionally merging with other black holes, slowly spinning faster as it absorbs matter and angular momentum from its surroundings. A black hole's spin, in fact, turns out to be one of its most important physical properties, second only to its mass. Some black holes have been measured spinning at rates approaching the theoretical maximum allowed by physics, dragging the very fabric of spacetime around with them in a phenomenon known as frame dragging, a real, measurable effect where anything near a rapidly spinning black hole gets physically twisted along with the rotation of space itself, whether it wants to or not. For most of the universe's history so far, roughly 13.8 billion years, this feeding, growing, merging, and spinning is essentially the entire story of a black hole's adult life. But black holes are not actually eternal, and this is where the story takes its strangest and most surprising turn. In 1974, physicist Stephen Hawking proposed something that seemed, at the time, to violate everything scientists thought they understood about black holes. Hawking showed, through a combination of general relativity and quantum mechanics, that black holes are not permanently black after all. Due to strange quantum effects occurring right at the boundary of the event horizon, involving pairs of virtual particles that constantly pop in and out of existence throughout empty space, black holes should very slowly emit a faint stream of radiation, now known as Hawking radiation, and in doing so, should very gradually lose mass over time. The mechanism behind Hawking radiation is genuinely one of the strangest ideas in modern physics. Empty space itself is not truly empty, even in a total vacuum, because quantum mechanics tells us that pairs of virtual particles, one matter and one antimatter, are constantly popping into existence, and then immediately annihilating each other everywhere in the universe, all the time. Right at the edge of a black hole's event horizon, however, something unusual can happen. One particle of such a pair can fall into the black hole, while its partner escapes outward into space. From an outside observer's perspective, it looks exactly as though the black hole itself has emitted a particle. And because the particle that fell ineffectively carried negative energy relative to the black hole, the black hole's total mass very slightly decreases with every such event. Do this often enough, over long enough timescales, and a black hole will very gradually shrink, radiating away its own mass, bit by bit, into the surrounding universe. Here is the almost unbelievable part of this entire process. For a typical stellar mass black hole, the rate of Hawking radiation is so unimaginably slow that it would take vastly, almost incomprehensibly, longer than the current age of the universe for it to evaporate away completely. Estimates for a black hole with the mass of our own sun suggest it would take somewhere in the range of 10 to the 67th power years to fully evaporate, a number so large it has no meaningful comparison to anything in ordinary experience. For the truly colossal supermassive black holes sitting at the centers of galaxies, the timescale required for Hawking radiation to fully evaporate them stretches even further, into numbers like 10 to the 100th power years or beyond, timescales so vast that our current 13.8 billion-year-old universe represents an infinitesimally small fraction of a single black hole's total lifespan. But here is the crucial detail that makes this story genuinely a complete life cycle rather than just an eternal, unchanging existence. As a black hole loses mass through Hawking radiation, something counterintuitive happens. Smaller black holes actually radiate faster than larger ones, because the intensity of Hawking radiation increases as a black hole's mass decreases. This means that in the extraordinarily distant future, once a black hole has spent an almost unfathomable length of time slowly shrinking, it eventually reaches a point where its evaporation begins to accelerate dramatically. In the final moments of a black hole's existence, after outliving stars, galaxies, and possibly even the last light in the observable universe, it undergoes a runaway process, radiating away its remaining mass faster and faster, culminating in an intense, final burst of energy, and then in the truest, most literal sense, simply ceasing to exist. No remnant, no leftover core. Just a final flash of radiation dispersing into the vast emptiness of an almost unimaginably old and cold universe. And then, nothing. This entire process, this full life cycle, is genuinely one of the grandest stories in all of science. A black hole begins its life in an instant of pure, catastrophic violence, the collapsing core of a dying star, or the direct collapse of a primordial gas cloud in the universe's earliest ages. It spends its childhood and adult life feeding on surrounding matter, glowing furiously as material spirals inward, occasionally unleashing jets of energy that stretch across galaxies, and sometimes colliding and merging with other black holes in events so powerful they visibly ripple the fabric of spacetime itself, ripples we have now directly detected here on Earth. It grows to sizes ranging from a handful of times the mass of our Sun to billions of times that mass, dominating the centers of entire galaxies and shaping how stars and gas move throughout them for billions of years. And then, after an almost incomprehensibly long period of stability, far longer than the current age of the universe itself, it very slowly begins to fade, radiating away its own mass through the strange quantum process Stephen Hawking first predicted, eventually vanishing entirely in one final burst of radiation, disappearing as though it had never existed in the first place. There is something almost poetic buried inside this science. Black holes are often described, casually, as the most destructive, most permanent, most terrifying objects in the universe, cosmic monsters that consume everything and let nothing escape, not even light itself. But the full scientific story reveals something far more interesting than a simple monster. A black hole is born from death, the death of a massive star. It lives a long, dramatic life defined by growth, feeding, and occasionally violent mergers with others of its kind. And ultimately, even the most extreme, most seemingly indestructible objects in the entire universe are still subject to the same fundamental rule that governs literally everything else that exists inside the flow of time. Nothing lasts forever. Not stars, not galaxies, not even black holes. We are living in a genuinely remarkable moment in the history of science, a moment where humanity has, for the first time, directly imaged a black hole's event horizon, directly detected the gravitational waves produced when two black holes collide and merge, and mathematically mapped out, with real scientific confidence, the entire theoretical life cycle of these objects, from the violent supernova collapse that gives them birth. all the way to the almost unimaginably distant future evaporation that will eventually bring even the largest supermassive black holes to their end. We are, quite literally, watching and studying the full biography of some of the strangest and most powerful objects the universe has ever produced. And the next time you look up at the night sky, remember that hidden among those stars, and at the very center of our own galaxy, there are black holes right now living out their own version of this incredible story, born in violence, living through billions of years of growth and transformation, and destined, however distantly in the future, to fade away into nothing at all. If stories like this, real science that sounds like it belongs in fiction, genuinely fascinate you, make sure you are subscribed, because we are going to keep exploring the most extreme, most mysterious objects in the entire universe, one incredible discovery at a time.